We'll talk here about beginning, kind of a beginner level 10 gigahertz system, and that's where a lot of folks start when we hear about them, although there are lower bands that we consider to be microwave, such as 90, you heard Kent talk about 900 megahertz, so 902, 903, 1296, another one that's very popular, 1.2 gig, 2304, very popular. For 3400. Now we've had to change from 3456 down to 3400, then 5670, and then we jump to 10. And so 10 gigahertz has this awesome propagation to it where there's a common volume out there that you can hit and illuminate with your signal, and a station on the other side of that can hear that. And it is a weak signal mode, but you know, it's not FM on a repeater. It is a weak signal mode, but you can make contacts, and it's really incredible. It's been a lot of fun for many, many people. So a lot of people come to us and they're in the 10 gigahertz, and then we can go up from there, but it seems that it starts with 10 gigahertz. So I'm gonna take you there. And so kind of the basic components, you'll probably hear this repeated a couple times. You have a 2-meter IF transceiver. You could use something other than that, like a 28 megahertz transceiver. The Down East Microwave 10 gigahertz transfer kit, very popular. There's one right here. This is actually a kit that I built, but you can save yourself some headaches and pay an extra $100 and have this shipped to you built. It was a pain in the butt to build, but you know, it taught me a lot, and I learned a lot and all that good stuff. And then you have to have a relay. There's some surplus relays right here you can get off of eBay. These are the ones. This is a 12-volt relay, and I think I've got a 24-volt. You're talking about voltages. 24-volt relay here. You got to watch out about latching relays because that takes a special driver. And then a dish or a horn antenna. And so those are the pieces. That's all there really is to it when you're in your most basic form. Now, you can do this a different way, and it becomes cheaper. And a lot of people have done this, and here's a picture of all the parts that it takes to put one together. And these are the filters and various filters and mixers, and there's that LNA, the SMA relay. And then there's a local oscillator and a multiplier. So those are all the basic components. This stuff's good to look at because it tells you how it works, and it's inside of these rigs that I've got on to demonstrate here. And it's inside this Down East microwave. They've just put it all together, save you the trouble, really even of understanding it. Here's a 2-meter multi-mode IF radio. This one a little older. It's the IC706. Got a lot of features that Bob liked here. Here's some of the more current stuff. I have used this old FT290 for years and years and years, if any of you remember this one. And then a KX3 will work, except that it drifts a little bit on 144 when you're in digital modes. So KX3 is a little overkill, if you will. Here's the radio, the IC705. This is the best choice overall, in my opinion. So of those choices, the ICOM 705, it doesn't drift on 144. Here's the inside of the DEMI transfer kit, so you can see a little bit more. See the pipe, what's called pipe cap filters. Those are real pipe caps that you would buy at the hardware store, but they've got a little probe that's coming up in the bottom that you solder in from the bottom. I think it's actually a pin, like a straight pin, that you cut to a certain length, and they've got a little guide there. You cut it to a certain length, like 5 millimeters. You shove it in on the other side of the circuit board, and you solder it. And then there's a screw adjustment comes down, and you're resonating a frequency, you're filtering there. So you're basically producing a filter that will pass a frequency through there. And this is what this board consists of, with various multiplication stages. So there'll be a filtration, which will drop some signal, right? Then there'll be a an amplifier stage that'll raise up the signal again, and then there'll be another filter that'll trim it down and clean it up a little bit more, and then amplifier, raise it up again. That's what's going on here. You'll hear us talk about the local oscillator, and that's an important concept to understand that, you know, in order to generate a frequency output, you've got to have a base of a frequency that is going to get you close so that when you add 144 to it, you pop out on the right frequency. Same thing happens on the receive. You're hearing, your rig is detecting the microwave frequency. How do you get it back down to 144 so far away in frequency? You mix that other higher frequency. So local oscillator really, and you could say, refers to that other frequency plus its multiplication factors. And it needs to be stable. It needs to be clean enough that, you know, you don't have to chase it too bad as far as turning the VFO. So you can see here the different pieces and parts. These, you've heard Kent refer to the rat race mixers. Those are right up in here. And these are the SMDs. Those are microwave, they're monolithic amplifiers. These are chokes, so they are filters too. This is looking at the bottom of the board, so you don't see the pipe caps that are on the other side. But that's what's inside this machine, this aluminum box here. There's some of those relays, like I've shown you. We've got a couple of examples here. You need a little hardline coax. You'll see some of that in use here on this transmitter. I'll pass this around, but you can see there's two pieces of hardline right here, just perfectly formed to get that relay suspended just right over the top of the case. Down East Microwave 10 gig kit. And we carry that. We built that, and then my buddy ended up buying another one, and we built a second one. And so we carry this one as a spare when we're out rovering. Here's a dish antenna. You see these all over the place. This particular one's an 18-inch. And there's the L&B that we heard about. Kent's got the angle, which is pretty important, the angle, which I'm going to talk about when we get to this dish here. But this angle from this support tube right here is important because, at least in my experience, if you've got all those parts the way that it was designed, it's going to be pretty right on as far as the focal point where your feed needs to go. Okay, so here was some information on getting a feed that would be at 10 gigahertz. So they study in these manuals and these books. There's the WR90 waveguide coax transition. Not a very expensive item. You can pick up on eBay, but this would get you to that point. He probably got these plans from Kent, but this is a feed horn. He's cut it out of a piece of surplus metal that looks like tin, and then he's folded it together and soldered it, and he soldered it onto what looks like just a flat flange here, and he's soldered it on there, and then he's bolted that to the waveguide transition. So now he's got a way to go back to coax, if you will, and transition it out to the feed horn, which will, you know, there's a design to this. There's science behind it, but usually you'll find these plans like on Kent's website or somebody's website, and they've already done this, but you got to think about, like, is it the right design for my dish? And so this probably had a 45-degree, you know, lobe within 3 dB power points, and that's about what you need with this kind of like an offset dish that we have over here. Here he's talking about setting the correct angle. So here he has copied, he's made a bracket out of aluminum. He's bent it, probably in a vise, and it's bent to the same angle as the L&B that came with the dish. And then he's added some slots and screws so that he can slide it all around and find the sweet spot. And this is kind of where we need to talk for a minute, because to find the focal point, there's an app for this, so don't freak out. But basically behind the app, which I'm going to show you, is you've got to be able to measure some dimensions. So you need the vertical length from ridge to ridge. You need the horizontal length from side to side. That really needs to be at the widest spot of the dish. And then you need the depth of the dish at this point. And then you need, from that point at the deepest point of the dish, you need that distance to the bottom lip, those 4 parameters. If you have that, you type it into the app, it tells you everything you need to know, like exactly how far from the top edge and from the bottom edge the focal point is. We're going to do that in just a second. I'm going to show it to you on this rig over here, which is brand new. And here's an online antenna book that's handy to use. Here's what he did to enter his dimensions. And you see, put in the diameter of the large axis of the dish. That's how high it was. The small axis is really not, I don't know that it's the diameter, it's the length. Then the depth of the dish at the deepest point was 45 millimeters. Distance of deepest point from bottom edge along large axis, 218. And you got the focal length is 256. So then he also got the tilt forward angle, which is important. You're going to go out and you're going to get your buddy to get on the air 25, 30, 50 miles away. And you're going to swing this dish back and forth and tilt it forward and back. You're going to hear him. It's no doubt. If you've got the feed anywhere near close, you're going to hear him. But to get it close as you can before you get out in the field, you need this tilt. So that tilt forward is how far does it tilt forward with respect to horizon? So this angle, is it 70 degrees, 62, is it 80? This would be 90. So call it the string and knot method, and that's what we're going to do here in just a minute. He had these numbers that came back from the calculator, 453 from the top edge, 256 from the bottom edge. Tie a knot. I use tape and tape the string or wire to the dish, and then where it comes down here, when you tighten the string, that's where your focal point is, or pretty darn close to it. So here he is with a yardstick, and he's got some duct tape he's holding on with, and you can see his string. You can see about where it's going to be knotted there. And then he put the station together here. So there's the demi transverter that I passed around, a sequencer below that. Sequencer will control the sequence of events that need to take place when you hit push to talk. So, for instance, you don't want to transmit your IF signal into your transverter until it has switched into transmit mode and the relay that controls the antenna has switched over to take transmit from the transverter. So a sequencer is important however you end up with it. I make my own, but this is a demi one right here, and there are many available. Then there's a little power supply here. That's probably a DC to DC converter. Pretty much simple. That's as simple as it gets. So it's not difficult. Parts are available. 10 gigs, fastest growing. North Texas Microwave can give you some help. Does anybody have a knife that I could cut a piece of wire with, very small wire, like 28 gauge?
They don't let me have anything sharp.
They don't let you have anything sharp? Okay, yeah, I want to be able to cut a piece of wire here. Let me get my glasses on so I can see. So we'll go down here and just talk a minute about, bring this up here. So this is the app, and I have the app on this computer, but I already ran the numbers, and I want to show you how I got them. But basically, this is the calculator. You can get it at this URL. Actually, there's a link at that URL, but Bob Atkins does a great job of giving an explanation. better than what I've done tonight. But you'll enter your frequency. This is 10 gig, 10386. You could put 47088 in there for 47 gig, but that's 10368. Diameter, large axis 913, small axis 850. Depth of dish at deepest point, and deepest point from bottom edge. All those numbers I've measured here, but I want to show you how I got them. So you'll think about this or remember it, and you know, it doesn't need to be intimidating or a problem. It does help to have a second hand on this, but I've kind of come to the conclusion that I'm just going to have to do it by hand myself. This dish is the next dish that I'm going to try, and the reason for it is my other dish, I was out and doing rovering a year ago in March, and the wind was up real high and it blew my dish over, and it blew my whole platform went over on on concrete sidewalk, and it wrinkled up this side of the dish pretty good, about that much of it just smushed in. And so when we go to some of our gatherings, we get Kent to come out, Kent Britton, and he measure our dish gain, and he gave me a really bad report on that dish. So I decided I can't be embarrassed like that anymore. I'm going to get me a new dish. So I got a new one. I got a bigger one because we're in Texas. And this one has some dimples in it, right in the bead that runs around. It's got dimples that mark the top center and the bottom center and the side, so it made it easy. You know, I didn't have to. So, but I did turn this thing upside down, and I put a marble in there, and it rolled around like a roulette wheel, and it finally came to rest in the center, and I marked it right here with a pencil. So I got a little X there. I'll save you all that trouble. So then you come in here and you get this measurement, and I'm on the millimeter scale, and you get this measurement to the bottom, and it looks like it's about, let's see, 900, and it goes off the scale, but it's about 915. So I think that's what I ended up with here. 973. Well, I can't see. Yeah, it's 973. So that's the top to bottom measurement. This one right here. This guy's example has these numbers, but I'm sorry, it's like this. So there's the 973, and then the 850 goes across side to side. So I got a dimple here, and a dimple there, and 850. So I know I got 850 across, and then depth at the dish at the deepest point, 78. It says this one I have to use. This is an extension for a race for cutting with a skill saw, and so I will put this across here like that from the point to the point, and then use some kind of a ruler that does not have. It doesn't have any space before it starts with the millimeter, if you know what I mean. The millimeter's right on the edge, and then I find my little spot, and I measure that, and I get my number. So now I've got that number, and then I just need the last number, which is the number from here to here. Relatively easy to get that number, and then I can input it in there. Now here comes the truth, because here's the string or the wire, and if we can cut it, my cutters are downstairs for tomorrow's demonstration. It should be somewhere, yeah, right there will be fine. If you can cut that for me.
Right about there?
Yeah. Ooh, that didn't take long, did it?
Nope.
So I would tape this to the top. After I measure, I'm going to make 2 marks on it. I've done this a few times, usually with a lot smaller dishes. But so what I want to do is I want to tape this to the top, but I want to measure it first and get that first measurement on here. And so I'll show you this once I get it done. There will be a mark. That marks where I want to tape it to the top. And then from that mark, I need the, here's the data. So the focal point is 537 from the bottom edge, 872.76 from the top. So you got to go 872. And like I said, you can just get close. In fact, I want to show you the monkey arms, because usually the next stage after finding this spot and figuring out how I'm going to put my feed out here on the end is I use these to hold the feed while I put a weak signal about 200 yards out by the front road on the highway, about 300 yards out down the driveway. And then I start moving this back and forth while I watch the signal strength. And then when I get it perfect, I've got these arms clamped to it. And the feed horn is going to be right here. This is the one I want to mount. So this is a dual band feed. It takes 24 gigahertz here and 10 gigahertz here. And when I find that sweet spot and that focal point, it will be perfect for both frequencies, because it doesn't matter. The focal point is the focal point is the focal point. So to get that, you can, these are just strong enough to hold this in position, and other smaller, I'm going to pass that around too, other smaller feed horns. But this is a dual, so it combines both frequencies together, and that is some kind of a yo-crunch plastic top that is the radome that somebody figured out fits that design just right. So we were at 872. Yeah, I can do that with this ruler without having to play any other games. So here we go, down to 872. Now I put that mark there, but now the job is to tie a knot right there, because the knot marks the spot. And then there should be some other value hanging off this other end. So there, I got it. And then now this other end is 537 from the bottom edge. So that comes from the knot. I have to go 537. But what you will find as the answer here when we get done is that the way that dish was designed and for use in a satellite sense, and where they have mounted this black shroud is damn close to where this knot's going to be. Of course, it'll have an L and B in it, so there's some protrusions that come out. But they're making these for money, and they didn't make a mistake. So what we're doing is kind of confirming for our own selves. What was it, 527? 537. So 537 comes to here. Now, the final is to get ready to tape the bottom and the top and see where this knot shows up. There's the black mark. There's the notch. Look at the knot. Knot's already telling us where it ought to be. And then here's the other black mark. I end up usually taping this down to the support arm because it'll hold better. And here we go. Look. Look where it shows up. Imagine an LNB in there. So we're right dead nuts on. And so then the next thing is the angle. So let's get the angle. The angle, I use one of these. I've had this thing for years. I don't even remember why I got it, but one of these, probably something, there's probably a name for this. It's like protractor is what I call it. But anyway, it says I need to tilt for operation with the main beam on the horizon with the feed at the bottom, meaning some people put the feed on the top. In Europe, they actually turn this upside down. But if, don't ask me, I don't know. But if the feed is at the bottom, the dish must be tilted forward so the large axis is 68.4 degrees above horizon. So I dial in 68. There it is right there. Tighten it up. And then using this extension that will go, you know, it's good and stiff and it won't move around on me. I just look at it like this. Actually do it from that side. And then set this to see how close I am. You know, it looks like I'm going to have to come up some. So this will have to be raised, you know, and there'll probably be a wooden block under that is what we'll end up with. Maybe even some door shims, you know, on the wooden block to get it just close as we can. But the easiest thing in the world is to tilt that, you know, the rover platform when you're out. You have to adjust a leg sometimes, but you just move it forward. There's no doubt the signal's there. You just peek it on the signal. So it comes out pretty good. There's, you know, I didn't tighten everything too tight here, but the tilt's not too far off. It has to be raised a little bit. But that's how that works. So I just want to quickly, 5 minutes more, and tell you about some of this gear here that I brought. Here's some local oscillators. We have these in what we call weak signal use, so we just carry this whole hard case out with us when we go rovering, and if me or my buddy thinks something's wrong, we just turn it on. It's got one switch on a power distribution unit that turns it on, and then we have 10 megahertz references fed into these because they'll operate without that, but you'll get a very precise frequency. This is one my buddy built. It's got an Arduino in it, so it actually will, it has programmed frequencies in it, so we can shift it without any delay and make it go to some of our favorite weak signal frequencies on 10 or 24 or even others. He's got several in here. He found that these SMA attenuators made a pretty good antenna on it. He discovered that one day, and there's a whole story behind it. And then this one is, this is the Downey's microwave. You've heard about these. This one is a Downey's microwave digital oscillator. It is currently set with these dip switches to give us a frequency that times 12 will come out on 47 gigahertz, and it's a good sounding signal. I can hear it several hundred feet away with a, you know, with a dish. So inside of here is a little small board that's inside the Downey's microwave that got passed around. So this is what starts the oscillation that gets multiplied. And so if you frequency lock this to 10 gigahertz, you're really getting the great start at stability. That's why these are, there's 10 megahertz references in here. They're just, there's a guy downstairs selling them for $5 each. They're just little OCXOs, oven-controlled crystal oscillators. Of course, we talked about the IF rigs. There's the old, there's the, you know, kind of a drift that would be a waste of money, a lot of money and tied up in that. Going from this side, here's a 1.2 gig Downey's microwave transfer. It's complete. It's all complete. All you got to do is hook an antenna up to it and your IF rig. And then if you want to run FM, or you want to run CW, or want to run WSJT, you do all that with the IF rig, with this rig, these rigs. They're just hooked in here, and there's an antenna attached. This has got everything in it. It's got the local oscillator and everything, and it's 25 watts. So it's a great little package. There's several bands available from down east that are like these, that run up from, this is a 1.2 or 1296. Here's a 2304 transverter built by DB6MT in Germany. These are really fine pieces of equipment. Got the German engineering, very small. Not cheap, but these are, old and have been around a while, and you can pick them up for a couple $100. This is a 10 gig, so this is equivalent to the Demi, but it's in this package. So it's very small. This one is 2 watts, so it's not weak. Here's a 24 gig. I got a story on this. I want to get on 24 gig, and there are 2 frequencies in America. There's 24192, which is our terrestrial frequency that we use when we talk to each other, like terrestrially. And then there's 24048, which you use for EME. The few people that are doing it on 24 gigahertz, but it's 24048 is worldwide accepted frequency allocation, where 24192 is only available in the United States. I ordered this by mistake, so I ended up with a transverter that I really couldn't use. But we opened it up and retuned some filters and got it to work. So it is workable, but you got to be careful what you order. This is a special local oscillator. This is like these over here, only about 5 times more expensive. This is the DB6 German-built local oscillator that's capable of running anywhere from 8 to 13 gigahertz. Why do you need this? You don't need it if you're in these low frequencies. Where you need it is where you're going to try to run 24 gigahertz, because you don't want to start, well, you would prefer not to start with low frequencies and then multiply them 12 times. You want to start with something that's much closer and very good and stable, and this is the thing that will do that. So this will give you a frequency that only has to be doubled to get to 24 gig mix with 144 megahertz. And on 47 gig, it only has to be quadrupled. So you see, it's the game of multiplication, how clean, and every time you multiply the frequency, it gets dirtier, and you get more, noise included in the multiplication. So, folks, there's a market for that because of that. This is my last item to talk about. I'm proud of this. This is 24 gigahertz, gets you on 24 gigahertz, about 2 watts. This goes to the antenna. This is the SMA relay that switches between transmit and receive. The center pole is the antenna, so one side it's receiving, the other side it's transmitting. There's a 10 megahertz oscillator here that this board needs. In between here, sandwiched, is a module. This module are being harvested in Poland, of all places, by a couple guys there that are taking them out of what's called outdoor units, which are backhaul 23 gigahertz rigs, transceivers, and they only backhaul like 5 to 7 miles, 10 kilometers is the only thing they're doing. So they're networked together around the country, and these are coming up surplus, and they'll harvest this module and sell it for about $70 on eBay. Well, another Polish guy came up with this control board, the green printed circuit board, and designed it with synthesizers, i.e. frequency generators, that took a 10 meg stable signal and a PIC on there, an AT Tiny 85, that could be programmed with Arduino code, and it would inject both of those synthesizers to arrive at the right frequencies to put this thing on ham band of 24 gigahertz. So we got involved with this as a club, and now we've ended up with 150 of these that we have sent all over the world. And I built 14 myself for folks that didn't think they could handle the SMDs, but we order these out of China, and the Gerbers are sent there with the bill of materials, and they take a couple weeks to build them. And then there's a few parts that this manufacturer never has, usually a couple small inductors, and I offer to buy those at Mauser and ship those with the board for a small fee, you know, the cost of getting it from Mauser. So that has turned into a year and a half now of effort to get people on 24 gigahertz, but it works, and we've made some great contacts. I've got a friend that made 150 kilometer contact with his 24 gigahertz rig, his Wavelab. This is called Wavelab because the module is Wavelab, made by Wavelab. And that's all I have. If you're around tomorrow and you want to see some of the other stuff, drop in and watch. It's going to be fun. I got started on that breadboard project, and I realized that a lot of my breadboard stuff I never even finished. I never made perf boards out of it. I've never made it permanent, and we're out using it. And I've got so many things, you know, that. And I started looking. Every time I looked anywhere in the shop, it's a breadboard, a breadboard. So I'm not very good at getting them to the next stage. We've done a few, and actually even manufactured PC boards. But most of the time, we build something because we need it on a breadboard, and then we're done, and you go to the next thing. And so, you know, Paul's got that, and Al's got that, and it's still a breadboard, but it still works, you know. And if it ever gets faulty, like the wire wants to come out, they just get out the hot glue gun and just spray it all over the thing, you know. So you could no way fix it if you ever had to, but there's a story behind that, so I hope to share that with you too. That's all I've got. Thank you for attending, and anybody got any questions?
Thank you very much.
You're welcome. Thanks for attending.